Okay, so today we are going to continue our discussion of vectors. This time around, we are going to talk about something called components of a vector or components of vectors. Okay, now a component of a vector is how much a vector is along a specific direction. So if you choose a particular direction, then you have a vector. Then you want to find out how much a vector is along that direction. What you're going to find is what is called a component of a vector. It's a special type of vector, except we know its direction. So that's what a component is. A component is how much a vector is along a specific direction. In this course, we are interested only in two directions. That is the x-axis and the y-axis of the xy plane. That's what these are the two directions we're interested in, the x-axis and the y-axis. Okay. The process of finding out how much a vector is along the x-axis or along the y-axis, that's what is called decomposing a vector or resolving a vector. So when you resolve a vector or when you decompose a vector, you carry out a process where you try to find out how much a vector is along the x-axis and how much a vector is along the y-axis. Okay. So a component here, like I've said, is the effective value of a vector along a particular direction. So the value of a vector along the x-axis, that's what's called the x component. The value of a vector along the y-axis, that's what's called the y component. So the x component, which is the value of a vector along the x-axis, is written like this. So if you've got a vector A, then you are interested in finding out how much is vector A along the x-axis, then you write it like this, where the A is the vector and the x is the direction in which you want to find out how much this vector is along this particular direction. So that's called the x component of a vector. The y component of a vector is written like this, ay, where a is the name of the vector and y is the direction in which you want to find the size of the vector. Okay. How do we find the component? It's quite simple. Okay. We find the component as follows. The component of a vector along any direction is the magnitude of the vector. So we need the magnitude of the vector, or we need the size of the vector, multiplied by the cosine of the angle between the direction of the vector and the axis we are interested in. So the direction we're interested in, which is the x-axis or the y-axis, and the direction of the vector. So the size of the vector, so vector A, whatever the size is, multiplied by the cosine. So in this case, for this one, ax, so we multiply vector A, the size of vector A, times the cosine of the angle between the x-axis and vector A. So there's that angle there between the x-axis and vector A, the cosine of that angle, we multiply that. Then the same thing is going to be done with vector with ay. For ay, for us to get ay, we multiply the size of the vector A times the cosine of the angle between the direction, which is the y-axis, okay, the direction, which is the y-axis, and the cosine of the angle. So we are going to look at an example where we work out components and see how this is done. So here we have a vector A. As you can see, this is vector A. It has got a certain size and it's pointing in this direction. And we also have the directions we're interested in. So we're interested along this, in this direction, the x-axis. We want to find out how much vector A is along the x-axis. We also want to find out how much vector A is along the y-axis. So from the definition of the x component and the y component, we'll start with the x component. Okay, so the x component, ax is the size of vector A along the x-axis. So how do we do that? So we multiply the size of vector A. So that is the A you are seeing here, the magnitude of the size of vector A multiplied by the cosine of the angle between the direction, this is the direction you're interested in, the x, and the vector. So the angle between the direction and the vector is this theta. So AX is obtained by multiplying A, then cos theta. Is this clear?
No, sir.
Huh? Is it clear how we obtain the x component of A? How much vector A is along the x-axis? AX. You multiply the size of the vector. You multiply the size of the vector
Clear, sir.
times the cosine of the angle between the direction, which is the x-axis, and the vector. This. The same thing can be done with the y component. So the angle between the y-axis and the vector is this angle here. This angle here, which is not marked, but you can see there is a space here. It's this angle here. Now the y-axis and the x-axis, they make a 90 degrees angle. So if from the x-axis to the vector A is theta, then the remaining angle, this angle here, is 90 minus theta. Okay, so for us to work out AY, we'll do the same thing following the definition of what a component is. We multiply. Yes, come in.
Sorry, sir, for the inconveniences. 100% is PHY.
Oh, next one. So we multiply. So for us to find how much vector A is along the y-axis, vector A along the y-axis, we multiply the size of vector A, which is the A, times the cosine of this angle, the cosine of 90 minus theta. Now, as I'm going to show here, so which is like this. So AY is equals to A multiplied by the cosine of the angle between the direction and the vector, which is 90 minus theta. Now, cos 90, then the cosine of 90 minus theta is the same as sine theta. So either you can do this or you can work it out like this, because this cos 90 minus theta is the same as sine theta. So normally, when we are working out the y component of a vector, we just do this. A sine theta. So if you are given a vector, okay, if you are given a vector, like in our case here, we have the vector A, then we have been given the angle the vector makes with the x-axis, like this. We can find out how much the vector is along the x-axis. Now, I want you to notice something. How much the vector is along the x-axis. You can see this red line, and you can also see the arrow. So you have a red line up to this far. That is the length of the vector. Okay, that is the magnitude. There is also the arrow there. That arrow is showing you the direction. So this component is a type of vector, except it's pointing in a very specific direction. Do we have a question? So this is AX. So AX is equals to A cos theta. Yeah. The same thing applies with AY. We know that AY is pointing up and it has got a certain length. So how much it is here, this side? So A sin theta, you can move it because it has got a certain size and direction. You can move it from along the y-axis where this one lies. You can bring it here. You have not changed anything because the size and the direction are still the same. These components are special types of vectors. Okay, they are special types of vectors which point in specific directions which we are interested in. The directions we're interested in is the x-axis and the y-axis. As you can see, so from this arrangement, so we have the vector A there pointing in that direction. Then you have what ax at the bottom there is equals to a cos theta. Then you have your ay occupying this area here, so ay equals to a sin theta. What we have here for ourselves is a right angled triangle. With this right angled triangle, we know that for any right angled triangle there is a relationship between the a, which is in this case is on the hypotenuse of this triangle, the adjacent and the opposite, and that relationship is Pythagoras theorem. So we can relate the size of the vector A to the components ax and ay. These three things, a, ay and ax, can be related to each other by using Pythagoras theorem. And that is how that brings in something which is very interesting, in that if you know ax and ay, you can get a from Pythagoras theorem, and that's how we obtain the size of any vector from the components. So you have got a vector. So if you have got a vector a, you know its size and the angle it makes. You can find how much it is along the x-axis, that is just a cos theta. You can also find how much this vector is along the y-axis, that is a sin theta. So if you know ax and ay, ax how much a vector is along the x-axis, and you also know how much a vector is along the y-axis, you can use this information to obtain the size of the vector. And how do you do that? By using this expression. The magnitude of vector A, written like this, the magnitude of vector A is equals to the square root of ax squared plus ay squared, where ax is the x component of the vector squared plus ay, the y component of the vector squared. This is how you get the magnitude of a vector from the components. So we are now doing the opposite. The first thing we did in that table, we had the vector, then we broke the vector down into its components, ax and ay. Now we are doing the reverse. We have the components ax and ay, then we are trying to rebuild the vector from its components. The only things we need when you're trying to rebuild a vector from its components are the magnitude and the direction. Now some people, I don't know whether up to this time they don't know how to switch off their microphones or what. Cosmas and Preston, I don't know if it's the first time you're attending these classes, but we want your microphones off because you're moving in your chairs and you're making noise. Then there's another person, Preston, we also need your microphone off. Okay, so like I was saying, if you know how much a vector is along the x-axis and how much a vector is along the y-axis, you can rebuild the vector from scratch, from the components, by using this expression, because the only thing you need for a vector is you need the size. So this expression is going to give you the size of the vector. The other thing you need is the direction. What angle does the vector make with the x-axis? That's the only thing you need. Now, if we look back at this triangle, if you have your ay, that is the opposite, then you've got your ax, that's the adjacent here. Then you're looking for this angle theta here. There is a relationship you can use, a trigonometric relationship you can use, which connects ay and ax to this angle theta, and that is a tangent. So you say tan theta, because tan theta is equal to the opposite divided by the adjacent. The opposite in this case is your ay divided by this, your adjacent AX. So in our case, you can also, apart from finding the magnitude of a vector from the components, you can also use the components AY and AX to find the direction in which the vector is pointing using the expression tan theta is equals to AY divided by AX. Are we clear on what these components are, how we get them, and how we can use components to rebuild our vectors?
Yes, sir. But we can't see the components.
Ati? You can't see
Sir,
the...
I can't see the components and the vectors, sir.
You can't see this image? Figure 4? Or you haven't downloaded the notes?
I have downloaded them, but I can't access them.
You can't what?
I can't access them right now so as to be following you as you are looking.
Are you seeing my screen?
Yes, sir.
Are you seeing what I'm looking at?
No, what you are looking at, I can't see. I can only see you.
Is that what everybody else is experiencing?
No. No, I can see what you're looking at.
Okay, so you need to probably refresh your whatever it is you're using, reload the page, or you can log out and try to log in again so that we can admit you in. Because what you're experiencing is
Okay,
not,
sir.
yes, it's not what everybody else is doing. Okay. All right. So we know how to get the components AX and AY. We know how to build a vector, the magnitude from the components. We also know how to get the angle theta. Now, there was one thing I want to point out about the angle. We measure the angles by conversion from the positive x-axis in an anti-clockwise direction. So an angle which is measured from the, so we measure from the positive x-axis from here. We measure angles from the positive x-axis, then we go in an anti-clockwise direction. Such an angle measured like this is a positive angle. If we measure an angle in a clockwise direction, then that angle is going to be negative. So all our angles in this course will be measured from the positive x-axis, then we go in an anti-clockwise direction. Okay. Now, the other thing, apart from just rebuilding a vector from the components, okay, we can use these components to carry out addition.
Sir, just behind what the angle, you have said something about angles.
Here, we measure the angle theta, which is what we use for the direction of the vector from the positive x-axis in an anti-clockwise direction. So we measure from the positive x-axis, then we move in an anti-clockwise direction. When we do that, this angle, we're measuring it from the positive x-axis here, then we go in an anti-clockwise direction, we consider that angle to be positive. If the angle is measured from the positive x-axis or from anywhere, then it's moving in a clockwise direction. Such an angle is going to be a negative angle. Are we clear? An angle measured in a clockwise direction is negative. Is that clear? Next, the other reason why we are interested in these components of vectors is because they make addition of vectors quite easy. Okay, we have already seen how to add vectors using that triangle vector business, which is quite tedious, and most likely you will not get the correct answer at the end of the day after putting all the work in trying to draw things properly. We have already seen how to add vectors this way, but most likely at the end of the day, I can assure you it's very highly likely that with this method of triangle of vectors, you might not be able to get the right answer, because you need to be precise and all the vectors need to be drawn according to scale, and that might be a challenge depending on what the size of the vector is, or where it's pointing, and how much how much graph paper you have. So we need to look for another method of doing this, of carrying out this operation a plus b, or a minus b, or b minus c, or b minus a. We need another method of doing this apart from using this triangle vector. Yes, we have got an idea of what a plus b might mean, but we need to be more precise, not just having ideas. And that's where components come into the rescue. Okay, now how do we use components? Okay, and this is what we explain here. So the first thing to do is, for each vector you have been given, for example, here we have got three vectors: vector A, vector B, vector C. So for each vector you've been given, you work out what is its x component, you work out what the y component is, as we have demonstrated. For example, for vector A, you find ax, then you also proceed to find ay. For vector B, you work out bx and you work out by. For vector C, you work out cx and you work out cy. For each of these vectors, if it's a vector, then it means that if something is a vector, then it means that we have given you the size of this particular physical quantity, and we have also given you the direction in which this particular quantity is pointing. So those two things have to be met. We have given you the size and also the direction in which the quantity is pointing. So for example, for vector A, if you're given the size of vector A and the angle at which vector A points or makes with the x-axis, you can work out this ax, that is going to be a cos whatever the angle is. Then ay is going to be a sine whatever the angle is. Then we move on to b. We give you what the size of b is and the angle it makes. So you're going to have bx, which is going to be b cos the angle. Then here we're going to have by is going to be b sine the angle. Then you do the same thing with c. We're going to give you what the size of c is and the angle it makes. This information has to be given to you. Then you work out cx. So cx is going to be equals to c cos the angle. Then cy is going to be c sine the angle. So you should be able to work out for each vector you've been given what is the x component of the vector and what is the y component of the vector. Now, how does this help us carry out addition? Well, it does help us carry out addition because, for example, here a plus b is what is called the resultant. When you add vectors or when you subtract vectors, what you get is a resultant. So this operation of a plus b, for a plus b, if we are to carry out, we are to add the vectors a and b, what we need to ask ourselves is, how much is a plus b going to be along the x-axis, and how much is a plus b going to be along the y-axis? Because that's what we've been asking throughout when you're dealing with components. How much is the vector along the x-axis? How much is the vector along the y-axis? So for a plus b, along the x-axis, a plus b is just equals to ax plus bx. We add the x components ax plus bx. So we find for ourselves how much a plus b is along the x-axis. Similarly, we do the same thing for the y-axis. We ask ourselves how much is a plus b along the y-axis. That is going to be equals to ay plus by. The AY, you already have it here. The BY, you already have it there. So it's a straightforward process. You just add the components of the vectors involved in the operation you're doing. If you're doing addition A plus B, so you add AX plus BX. That tells you how much A plus B is along the x-axis. Then AY plus BY, that tells you A plus B, how much A plus B is along the y-axis. If you know how much A plus B is along the x-axis, then you know how much A plus B is along the y-axis. You can use Pythagoras theorem to find A plus B. You can also use that tangent thing, tan theta equals to AY divided by AX, to find the angle which this vector makes. Are we clear? Are we clear with what I'm saying, what I'm talking about? Why am I not getting confirmation whether people are understanding or not?
Yes, sir, we're clear.
Next, we move on to A minus B. This is a subtraction operation. For A minus B, we want to find out how much A minus B is along the x-axis and how much A minus B is along the y-axis. And how do we do that? We just work out this AX minus BX. This is going to give us how much A minus B is along the x-axis, and this one AY minus BY, that is going to give us how much A plus B is along the y-axis. Is this clear? For A minus B, so you subtract AX minus BX, that gives you how much is A minus B along the x-axis. Then this one for the along the y-axis, AY minus BY. Then you do a similar thing for B minus A. For you to work out B minus A, you work out, you're asking yourself, for this one you're asking, because this is going to give you a vector. When you're adding vectors or subtracting vectors, you get a vector. So this vector B minus A, how much is it along the x-axis? So that is going to be BX minus AX. Then along the y-axis is going to be BY minus AY. Okay? Is that clear? On how you add two vectors, A plus B, A minus B, B minus A. Are we clear? Before we move on. Okay. You are not restricted to only adding two vectors or subtracting two vectors. You can add as many vectors as you want, or as is necessary, or you can subtract as many vectors as is necessary. As I'm showing the next example, I add three vectors: A plus B, vector A plus vector B plus vector C. This is a vector because I'm adding vectors, so I end up getting a vector. So I want to find out how much is A plus B plus C along the x-axis, and that is going to be AX plus BX plus CX along the x-axis. Okay. Then again, I want to find out how much is A plus B plus C along the y-axis. That is going to be AY plus BY plus CY. So you straight away find out how much a particular vector is along the x-axis and how much a particular vector is along the y-axis. Once you have this information, once you have how much a vector is along the axis, once you have this, how much a vector is along this, and how much a vector is along there, then you can get this vector. You can get any vector. You can get any vector. Okay, once you know how much a vector is along the x-axis, and how much a vector is along the y-axis, then you can get the size and the direction of any vector. You are not restricted to doing only addition of a lot of vectors. You can do a combination of addition, a plus b minus c. So in this case, again, this is going to give you a vector. So the vector a, how much is a plus b minus c along the x-axis? That is ax plus bx minus cx. This. Then how much is a plus b minus c along the y-axis? That is ay plus by minus cy. We're done with this thing about components, and already you can see how how easy it is. This is much quicker to do, okay, than sitting with a ruler and a compass and a protractor trying to draw these lines which you're not even sure of if they're going to meet or not. Because from these components, from the x component and the y component, if you do this for each of those components, if you do this, ax squared, the x component squared plus the y component squared, then you run a square root over that, you get the size of the vector. Then if you do this, the y component of a particular vector divided by the x component, then you find the angle. You get your tan theta. Are we clear?
Yes.
Do we have any questions so far? On how we do vector addition. The next thing we're going to look at is an example. We'll start looking at this example. So under addition of vectors using addition of vectors acting along different directions using a table of components. So we have got three vectors, vector A, vector B, and vector C, which have magnitudes 20 meters, 30 meters, and 100 meters. Those are the magnitudes, 20 meters, 30 meters, and 100 meters. So vector A has got a size of 20 meters. Vector B has got a size of 30 meters. Vector C has got a size of 100 meters. Then vector A makes an angle of 45 degrees anti-clockwise with the positive x-axis. Vector A makes an angle of 45 degrees anti-clockwise with the positive x-axis. Vector B makes an angle of 120 degrees, again anti-clockwise with the positive x-axis. And vector C lies along the negative x-axis. This information about the sizes of the vectors A, B, and C and the angles they make with the positive x-axis is what is shown here. So I have my xy plane in blue there. So this end, that's what I've chosen to be the positive x-axis. Then the other end is the negative x-axis. The top part here is the positive y-axis. The bottom part here is the negative y-axis. This black line is my vector A. It has got an arrow. That's how we show a vector. A vector has got a line showing you the magnitude of the vector and an arrow showing you the direction in which this vector is pointing. On top of this line, I put the name of the vector, that is vector A, and I also put the size of the vector, 20 meters. So this shows you that this vector A, which is equal to 20 meters, is actually a displacement. A displacement is a distance covered in a specific direction. Then next, I show information with this angle in black from the positive x-axis, an angle of 45 degrees. So I show that this vector is actually pointing in a particular direction. That is enough to describe a vector. We need to know the name of the vector, how much is that vector, and in what direction the vector is pointing at. In the case of vector A, the size of the vector is 20 meters, and it makes an angle of 45 degrees with positive x-axis. That's a black one there. Then we move on to vector B. Vector B is this green line here. Again, it's a line with an arrow at the end. That's how we show that we are dealing with a vector, because vectors have got direction and size. Now, you will notice that this vector A and vector B, as much as their distances, I don't think they're drawn to scale, but that doesn't really matter, because on top of this vector, you put the name of the vector and you tell us exactly what the size is. So in the case of vector B, it is 30 meters. So it doesn't matter whether vector A and vector B, when I was drawing them, they look the same length. It doesn't really matter. I've specifically said vector A is 20 meters, vector B is 30 meters. So it doesn't matter whether you draw these things to scale or not. They are just sketches. Okay. Then you have vector C here. Vector C has been drawn in red. It lies along the negative x-axis. So this is what we mean by lying along the negative x-axis, like that. As you can see, vector C has got a size of 10 meters. And for it to lie along the negative x-axis, it needs to make an angle of 180 degrees from the positive x-axis. So these are the three vectors, A, B, and C, which we are going to be dealing with. Are we clear on what A, B, and C actually look like on the sketch when sketched on the XY plane? Okay, so that being the case, the next thing, like we have done, where was that? Like we did here, the next thing is, like we did here, the next thing is for A, B, and C, we need to find what is the x component, the y component for A and B, the x component for A, the y component for A, the x component for B, the y component for B, the x component for C, the y component for C. We need to find those. And that is what's happening in this table here. We are working out the components of vector A, vector B, and vector C. We know, like I said, for you to work out the components, you need to know what the size of the vector is, and you also need to know the angle it makes with the x-axis. So in the case of vector A, so you draw a table. That this table is going to have a column for vectors, the vectors you're dealing with. Then you're also going to have another column for components. Then it's going the x component. Then it's going to have another column for the y components. Then we start. So for vector A, here, vector A, we want to find AX. So AX is the x component of vector A. Or in other words, we are saying how much is vector A along the x-axis. So AX, how much is vector A along the x-axis? For us to get that, we know that the x component is A cos theta. So the A is the size of the vector. So A has got a size of 20 meters multiplied by the cosine of the angle. The angle is 45 degrees. So 20 meters multiplied by cosine of 45 degrees, that gives you approximately 4 meters. So the vector A along the x-axis has a size of 14 meters. Then again, we move on to AY. How much is vector A along the y-axis? So that is going to be A sine theta. So the size of the vector, 20 meters, multiplied by sine 45 degrees, and this gives you 14 meters. So at an angle of 45 degrees, as you can see, at an angle of 45 degrees, the vector A along the x-axis is 14 meters, along the y-axis is also 14 meters. This is quite interesting to note. We move on to vector B, and these are positive. So this is positive 14, meaning that these components are pointing in the positive x direction. Here, if you look at these, the components are pointing, the first one, the x component, is pointing in this direction. positive x direction, the y component is also pointing in that direction. It makes sense considering where A is. Do we have any questions on how you work out the components of A? Is it clear on how the components of A are worked out and what they mean?
Please repeat your explanation.
Ati?
Would you please repeat how we work them out?
Are you seeing what I'm saying?
Yes.
20 meters times cos 45 degrees.
Yes.
What is the 20 meters?
The 20 meters, that's the size.
Yes, the size of vector A. Then the cos 45 degrees, the 45 degrees, what is it?
The angle from the x-axis.
Yes. That's how you work out the x component of any vector. You multiply the size of the vector times the cosine of the angle it makes with the positive x-axis. When you move on to the y-axis, the y component, ay, you multiply the size of the vector times the sine of the angle the vector makes with the y-axis, sorry, the x-axis. Are we clear?
Yes.
Yeah, that's the process we're going to be following. We do the same thing for B. We don't change. B, we want to find out how much Bx is. Bx is how much vector B is along the x-axis. So we multiply the size of vector B. Vector B is 30 meters. Then times the cosine. The cosine, the angle is 120. So 30 meters cos 120, that gives you minus 15 meters. Minus 15 meters. So this is telling you that actually a component can also be negative. What does that mean? It means that along the x-axis, this Bx is pointing in this direction, along the x-axis. This Bx is pointing along the negative x-axis. It's pointing this direction. Are we clear? That's what a negative component means. Yes. Then we work out By. So By is equals to 30 meters, which is the size of vector B, multiplied by the sine of the angle. The sine of the angle is 120, so 30 meters times 120, that gives you 26 meters. Is that clear?
Yes.
Next, you work out for C. For vector C, you want to find out what is the how much is vector C along the x-axis. So that is Cx, the x component of C. Cx is equal to the size of vector C. Vector C has got a size of 10 meters multiplied by the cosine of the angle. The angle it makes, vector C makes with the positive x-axis, is 180 degrees. So 10 meters multiplied by cos 180 degrees, that gives you minus 10 meters. So this is a case in which, as you can see, the size of the vector is 10 meters. Along the x-axis, it's minus 10 meters. So the minus is telling you that the x component of this vector is pointing along the negative x-axis. Then for Cy is going to be equals to, Cy is how much is vector C along the y component. So this is going to be, you multiply the size of the vector, 10 meters, times the sine of the angle, sine 180 degrees. So 10 meters times sine 180 degrees, that gives you 0. So in this case, for vector C only exists along the x-axis, and it points in the negative x-axis. There is no part of vector C which points in the y direction, y-axis, and you can see it from the way vector C has been drawn. Vector C lies completely along the x-axis. There is no part of vector C which lies along the y-axis. Are we clear?
Yes.
Okay, so we have managed to do the first part of the job. That is finding out how much, what are the components. of each of the vectors we have. How much is AX? How much is AY? How much is BX? How much is BY? How much is CX? How much is CY? So when we meet tomorrow, we are going to use these components to carry out the addition, the operations A plus B, A minus B, B minus A plus B plus C, A plus B minus C. Hopefully we can do this tomorrow so that next week we can shift camp to another topic. Do we have any questions? We're going to stop here.
No.
Are there any questions?
Sir,
Yes.
Are we writing a test in physics?
Ati?
Are we writing a test in physics as well next week?
Next week?
Yes.
Are you writing a test as well in physics next week?
Yes.
I don't know. No, I don't think so.
All right. Okay. Thank
You haven't learned much in physics. There's nothing I've really learned. You're just getting started. So it's pointless giving you a test now. Any other questions?
thank you very much.
Okay. Any other questions? Okay, so if there are no other questions, let's meet tomorrow, same time, and let's wrap this thing up. Okay, so I'll see you tomorrow. I'll stop sharing my screen.
Bye, sir.
Cheers.